So if we take the idea of a vector and just kind of take that next step and look at the vector components. So we have the component in terms of 3 dimensions. We have the component in the I direction, the J in the J direction, in the Cartesian 2-dimensional plane. So this would be 2-dimensional. And this would be an I, J, and a K component in the 3-dimensional plane. And that should be an X right there. So then we can, instead of having these be constants, we can have these be functions. And so they can change with respect to an independent variable, such as time. So when we talk about this position vector here, it can change with respect to time. And so as we kind of progress through time, that you will see this vector kind of moving and redirecting itself in the 2 or the 3-dimensional plane with respect to time. So I keep referring back to this independent variable time. So what we have then is we have ourselves set up with a set of parametric equations to describe our our x, our y, and our z position as a function of time. So we go back to that world, that happy world of parametrics, where we can work with those parametric properties. So let's first talk about domains and range and stuff like that. So let me just kind of grab this picture here of the 3-dimensional plane. There we go. Okay, so let's just kind of bring it into here, and we can talk about that in terms of range and domain. So if we talk about this vector valued functions range and domain, the x component here is the square root of 4 minus t squared. So we're talking about the possible values for along the positive and negative x axes that are defined. And so when we look at this, we know that square roots can't be less than 0, or we can't be negative value. And so if we set them up where we know, in fact, I should restate that we know that the quantity has to be greater than or equal to 0, then we can figure out what values of t lead to real answers. And so that's 4 minus t squared being greater than or equal to 0, which means t now has to be less than or equal to 2. And so in order for this to be valid, and so when we're looking at, there's the value 2 on the x coordinate. So in other words, if I go out, I should restate that if I progress through time, through 3 seconds or through 4 seconds or through 5 seconds, then this does not become a real solution. So we have to keep our time under 2 seconds. This component can be anything, basically. If we're talking about time, then this has to be greater than 0 as well. And then likewise, 6t can be anything. And again, if we're talking specific to time, then t would have to be greater than or equal to 0 unless we want to look back in time. So then when we talk about finding the domain of the vector, then we have to stick with the most restrictive conditions. So we take a look at this and we say, well, this can be true. We have to stick with t between 0 and 2, but we could also stick between 0 and negative 2 and be okay as well. So that being the case, then this actually gets changed to a negative 2. And so and since these don't have any restrictions at all, we have to stick with that most restrictive condition. So the domain then is going to be values that are between -2 and 2 as values that will work. If we take a look at this one, the conditions kind of change a little bit. We have a vector valued function r, and its x component is cosine of t. And so when we think about that, the domain here for cosine, we're talking about from -1 to +1, as we are also for sine. So this domain here is going to be between -1 and +1. I'll use the interval notation like this. And so and so those will be for all values of t being in radian values. So this is really not among the options of what we need to evaluate, but if we would evaluate the vector at pi/4, then that would be the cosine of pi/4 I plus 2 times the sine of pi/4 j. And so the cosine of pi/4 is square root of 2/2. So square root of 2/2 I plus 2 times the square root of 2/2 j. So doing the math here, we get square root of 2/2 I plus the square root of 2j as the vector at pi/4. And then if we take a look at this function here, we see the characteristic form of an ellipse. We've got denominators that are not the same. And we know that the center is 0, 0. And we want to represent this by a vector valued function. So we want to represent this somehow in a parametric term where we have an x of t I component and a y of t j component is kind of what we're going for here. And so if we think about then taking one of these, and if we remember that when we create vector valued functions, we're creating a parametric, and we did this a little earlier. We talked about parametric functions where we could create several parametric functions that were equivalent. And so we just have to define what our independent variable should be. And so the easiest thing to do is just call your independent variable t, and then solve this for y. Then you can just go ahead and plug in t where you see an x. And so solving this for y then means bringing this to the other side. So we end up having y squared over 9 equals 1 minus x squared over 16. We'll multiply through by 9. And take the square root. So when we take the square root here, we end up with a plus or a minus, and that's important because we have a situation here where we have a conic section, and so we don't really have this in itself is not a function. It wouldn't pass the vertical line test, but we can represent it as a vector valued function. And so we have to represent it as a family of vector valued functions. So for instance, we would have r of t, maybe the upper portion of the ellipse. So it would be t, and then expressing this in terms of t is just rewriting it and pulling out the x variable and putting in the t variable. And so so the vector valued function here for the top half of this curve would be t in the I direction plus, because we'll take the positive root, that would be the upper portion of the ellipse, 9, 1 plus t squared over 16. And then the below the lower half of the ellipse, maybe we'll call that s of t, would be t in the I direction minus the square root of 9, 1 minus t squared over 16. So there would be the two parametric vector valued functions that represent that ellipse. This is similar to talking about the domain and the range. When we have a vector valued function, it doesn't matter if it's two-dimensional or three-dimensional. If we want to find the limit of that function, we just need to see what the limits of each piece are. And those become the limits of each component, and that becomes the limit in total. That becomes the limit of the entire vector valued function. So let's just take this one component at a time. The limit as t goes to 0 of e to the t, that's determinant. So we can just go ahead and plug in 0 here. That equals 1. The limit as t approaches 0 of sine of t over t, that's indeterminate. That's 0 over 0, so we need to do a L'Hopital's here. So we'll differentiate the top and bottom. Derivative of the sine is cosine of t. Derivative of t is 1. And so as t approaches of 0, this also approaches 1. And so, yeah, again, we talked about these components changing based on the value of that independent variable t, that parametric variable. So the idea is, as this function is changing in value, you can picture that function. We'll provide a picture in a little bit. Let's just find this last limit here. So the limit as t approaches 0 of e to the minus t is going to be e to the 0, which is determinant, and that is also 1. And so they don't have to be the same value, but they do happen to be the same value for this instance. So we're talking about, and the limits can approach different values, and the idea is the limit of the whole function is just these three components. So the limit as there we go. The limit as t approaches 0 of this entire function, e to the ti plus sine t over t j plus e to the minus t k, is 1i plus 1j plus 1k. It's the individual limits of each one of the components. So what does that mean? Well, if we draw our three-dimensional graph here, so there's our positive x, there's our positive y, there's our positive z, and at time t equals 0, this vector approaches a value of, so at t equals 0, this vector is approaching a value of 1, 1, 1. So where is 1, 1, 1? Well, it's over 1, it's out 1, and it's up 1. So, it's a little hard to see on this grid, but this value is approaching that portion where we're out and over and up, kind of floating here in that first quadrant, so to speak. And so you can kind of picture that this terminal point, as t changes with respect to time, is going to start to float away from that value. Well, we've talked about domain of a function. We've talked about the limit of a function. We can also talk about continuity. And so when we're talking about continuity, we really are just testing to see if the limit exists. So if we're continuous at a point A, then the limit as we approach A is going to be whatever the value of that function is at A. And so when we talk about where this is continuous, again, we're talking about where can these values be real and defined. And so we just take it component by component, like we've done in the past couple of sheets. We know that when we take the square root of a number, that number has got to be positive to get a real solution. And so our t values better be greater than or equal to 0 in order to get a defined solution. As we take a look at this again, we have that same characteristic of a square root. This can't be less than 1, because then this whole thing will start to become negative, and so for the same reasons, this value has to be greater than or equal to 1 at all times. And so what we have is kind of a situation where one component might exist where the other component doesn't. So, for instance, at t equals 0, the I component exists, but the j component is undefined, or is not, or maybe the better thing is to say it's not real. It's complex. And so that being the case, if one of the components is not continuous, then the whole thing is not continuous. So R of t would be not existent or not continuous at that point in time, so to speak. So when we come back and look at this from a continuity standpoint, we have to pick that most restrictive condition. And that most restrictive condition is this t is greater than or equal to 1. So that kind of governs the whole vector valued function. In other words, we can include 1 and we can go up to infinity, but we can't go less than 1 because at that point this one does not become a real solution anymore.